Hello guys, welcome back to my channel Gamma Digamma. It's been another big break. I apologize for that. There's just been so many things going on and I had to sort of resolve that what I was gonna make a video on. And now I know what I'm gonna make a video on, so I'm here with more content. Finding content is hard these days. But regardless, I'm here and let's get started. I have a fantastic problem for us to do today. So consider an infinite sum which I will appropriately call S to be sum from n equals 1 to infinity of digamma of n over n squared. So it's appropriately an infinite sum of the digamma function. Now, one thing we can do looking at this is to write the digamma as the n minus first harmonic number minus Euler-Mascheroni constant. This is a well-known formula, by the way, following from the infinite series representation of the digamma function and the definition of the n minus first harmonic number. So once we do that, we can write S nicely as sum n equals 1 to infinity of n minus first harmonic number over n squared minus the Euler-Mascheroni constant over n squared, and I will bracket that because I do not want angry comments under this video. So I mean everything so far has been natural and logical. Now what I can do to make our life a little simpler is recall the definition of the nth harmonic number. So the nth harmonic number, h sub n, sum from k equals 1 to n of 1 over k, and the n minus first harmonic number is defined as sum k equals 1 to n minus 1 of 1 over k. So if I add a 1 over n to the n minus first harmonic number, I get the nth harmonic number. This is just sort of like a recurrence relationship. You can you can figure this out judging these two definitions, these infinite series definitions. So okay, with that setup, we can sort of rewrite this S a little bit just to sort of maintain the same n and n on top and not have an n minus 1. We can substitute for h sub n minus 1 because h sub n minus 1 is h sub n minus 1 over n. Once we do that, we sum from n equals 1 to infinity of h sub n, nth harmonic number, over n squared. So you see I have n and n on top. So this is just to maintain a constancy uniformity in terms of the indices of summation. Another sum will have the 1 over n factor and the n squared. So I have an n cubed down there. I'm just substituting everything in, minus Euler-Mascheroni along with this 1 over n squared that's being summed from, maybe I'll write it for this step. Now we can significantly simplify some things. Well, the nth harmonic number over n squared we will have to do a lot of work on that. Meanwhile, the 1 over n cubed sum from n equals 1 to infinity is just the Riemann zeta of 3 minus Euler-Mascheroni times the Riemann zeta of 2. This is our simplification so far. And now what we aim to do is to sort of evaluate, simplify, or find, to be more precise, find a closed form for this underlined blue term. So I'm going to do that on a relatively fresh page. So as you can see, I've appropriately labeled the sum we need to work on S1, the sum from n equals 1 to infinity of the nth harmonic number over n squared. Now to do this, this solution that I have here It's not really something I constructed with. It's really elegant, it's really beautiful. I wouldn't trust integrals so much. But the way to do this is to convert this infinite sum into an integral, especially the 1 over n squared. How can we represent that as an integral? Well, consider, I don't know, maybe call this a lemma or something, because we're going to use this later. So call this a lemma. Maybe just lemma. Consider negative integral from 0 to 1 of x to the n natural log of x. That's horrible. I can do a better job with that. Dx. Well, why have I considered this? Why is this so arbitrary? How do I work with this? Well, because you can write this integral 0 to 1 x to the n minus 1 natural log of x dx. We can use integration by parts, differentiating like the natural log, of course, while we integrate the other bit. You have minus x to the n over n natural log of x 0 to 1 plus integral from 0 to 1 x to the n minus 1, because the natural log differentiated brings down an x, over n dx. Well, for at 1, natural log of 1 is 0, so it goes to 0. At 0, we have to sort of do a L'Hopital's rule kind of argument, but even this entire thing goes to 0, so we don't really need to worry. You can check it out, do it on your own if you want. And this can simplify to 1 over n squared x to the n from 0 to 1, which is exactly 1 over n squared. So we have found an integral representation for 1 over n squared. And we can plug this in back into S1 promptly, holding nothing back. So S1 under the lemma is just going to be sum from n equals 1 to infinity of nth harmonic number, and then we're going to have, I think, a negative integral from 0 to 1 x to the n natural log of x over x dx. Now I urge you to remember this extremely important formula that I had sort of proved in a previous video dedicated solely to harmonic numbers. So that formula, that video, I probably would add a card there by now. Formula goes like this: sum from k equals 1 to infinity of z to the kth harmonic number is just minus natural log of 1 minus z over 1 minus z. Well, of course, absolute value of z is like less than 1, and it's just basically in the radius of convergence. So I don't need to put like an absolute value inside. So I can totally use this. In our case, we have an x to the n and an h sub n instead of a z to the k and h sub k. So that's the only difference. We can use this directly, and S1 then becomes, I'll probably just make it a little more clear. So I'm gonna have x to the n. Maybe I should do this inside the integral. I have x to the n h sub n natural log of x over x as it is dx. So you see this term I'm underlining, that's basically this term over here. So we can just and the sum, maybe we can move the sum inside as well, of course, assuming all those nice things. Yeah, now we can totally use the identity because we moved the sum inside. Again, assuming uniform convergence and all that analysis kind of fancy thing. So this entire thing is just this thing over here. So we can just substitute this instead of the infinite sum in blue. So we have minus integral from 0 to 1. Instead of z, we have an x. So just make the appropriate changes. We have a plus from the two minuses. Natural log of 1 minus x, natural log of x divided by x times 1 minus x dx. So our infinite sum that we were considering has become a pretty proper integral. It's not even improper, I would say. Maybe you can make it improper. I mean, it has some divergences at 1 and 0. So it's an open interval 0 to 1 basically, but it's completely become an integral. Now what's the advantage of doing this? I don't really trust my integrals unless there's something really, really special going on. Now the first thing I can do to evaluate this, and trust me, this can be evaluated, is sort of split the denominators separately using partial fraction decomposition, such that integral from 0 to 1, natural log of 1 minus x, natural log of x divided by x dx, plus some splitting the denominators up using partial fraction decomposition. I'm skipping some algebra. Maybe I can make some space here for myself. Natural log of x divided by 1 minus x dx. You can see you can cross multiply and you can see that you're going to end up with the same expression as S1. So there's indeed equality. Now how is that helpful? That's helpful because there's like an unset symmetry between the two halves. So let's just consider this the second term here. So if I say y is 1 minus x, dy is minus dx, after doing some simplification, I'm going to end up with integral from 0 to 1, natural log of y, natural log of 1 minus y divided by y dy. I've accounted for the sign flipping and upper and lower bound exchange. And I'm going to have this term as it is because I didn't really do anything to this term. And since this is a definite integral, the variable of integration does not matter. Both of these things are equivalent. So I can just have 2 times one of these. Okay, that's fair enough. Now what can I do? What I can do is let's see. I can use the Taylor series for the natural log because we're inside the region of interval of convergence 0 to 1. Use the Taylor series for the natural log of 2 times integral from 0 to 1, sum from n equals 1 to infinity of, well, let's see, minus 1 to the n plus 1, and we're going to have a minus x to the n over n, natural log of x over x dx. So this minus 1 to the n minus 1 to the n will sort of be positive always. So we just have a negative like that. Sum from n equals 1 to infinity. We have x to the n minus 1 over n and the natural log of x dx. We can shamelessly interchange the sum and the integral. Again, assuming all those uniform convergence, piece by piece, term by term integration in the infinite series. But whatever we do, we're going to end up with this expression, which we can definitely simplify. And what's the simplification? Well, just integrate it out. Integrate by parts, to be precise, like we did for the lemma. So we're going to have an n squared term because of integrating that. So we have x to the n natural log of x from 0 to 1 minus integral 0 to 1 x to the n over x because you differentiate the natural log dx. If you don't, if you can't like follow up as quick, you can just pause the video, do it on your own. I urge you to do it on your own actually. because I just want to save time. I don't want to extend this video too long. Well, at 1, natural log of 1 will make it 0, so it's gone. At 0, you can work the L'Hopital's rule out. N is always going to be greater than or equal to 1. So using that, entire thing goes to 0. The minuses cancel each other out. We have this 1 over n squared like that. And then we're going to bring down another n, x to the n from 0 to 1. This becomes 1. We have an n cubed. So we have 2 times the Riemann zeta of 3. That's what S1 evaluates to. This guy here is 2 times Riemann zeta of 3, believe it or not. And what was S1? Let's go back. Where's S1? Yeah, there it is. It's 2 times the Riemann zeta of 3. Now we can tie all these things together. We can go back to what our original problem was. Our original problem was, I believe, sum n equals 1 to infinity. We had the digamma of n over n squared, which we sort of said equal to S1, which was the harmonic sort of version of this, h sub n over n squared as the summand. And we had the Riemann zeta of 3 minus Euler-Mascheroni times the Riemann zeta of 2. We found what S1 is. It's 2 times the Riemann zeta of 3. Everything else is unchanged, unaffected. We're going to end up with the Riemann zeta of 3 minus Euler-Mascheroni times Riemann zeta of 2, which is the Basel problem, pi squared over 6. And this, boys and girls, is the answer you were looking for. We've solved the problem. It's one of the most, elegant solutions. You won't really catch them easily on your own. I wouldn't have done this on my own. I had to refer to some, places where this was used. The Nearly Impossible Integrals book by Valian. It really teaches you when an integral representation is really helpful. In this case, we had this nifty property right here. This nifty property in yellow, in dark yellow, in chrome. This property I had proved, but I had forgotten. To prove this, you need to expand the kth harmonic number in terms of its integral representation, which is based on a finite geometric series version. So please watch that video. So it all relied on this, and also this really beautiful lemma. So I'll keep in mind to use this, so this means integrals are also an important tool in our arsenal when we want to deal with infinite sums.